Good evening to you. This is Galactic on the 4th day of November of 2022, broadcasting from Chico, California, our science presentation series, which has been running now for close to 6 months. So here's what we're going to study tonight, is the Dirac equation. The Dirac equation is legendary now. And if you don't know anything about it, don't worry, nobody does. Only Paul Dirac knew anything about it. And he's gone now. But what I'm going to teach you how to read this stuff so you'll actually know what these things are trying to say. The knowledge is in there, and I'll show you where it is. But look at that equation. That equation looks like it's a well-formulated equation. It is, as long as you know what each and every one of those symbols means. And once you do, which will take you 16 years, and I'll show you a quote where it says that. It actually says you're going to need 4 years of advanced calculus to understand this equation. I'll show you what it means in under 10 minutes. First of all, you have to know how to read it. And it's fairly simple once you have a kind of a guidebook where to start. You start here on the right-hand side. This thing, the squiggly DT, you can scratch it out. It doesn't mean anything. Technically, it means a partial derivative. But that is implied, and it doesn't need to be there. There are 3 terms on this side. You can erase these 2 D's and this T and take this line out of here. This is called psi, and it's a function. Technically it's the result of the function. But you'll notice that the function is on both sides, and so this is an identity equation. And the reason I say that is this psi is in the numerator. So this is the imaginary number, this is the reduced Planck constant, and this is the function psi. On this side we have the function psi and a coefficient for it. So there are only 3 terms in this equation. Psi, psi, and the coefficient. And now I'm going to tell you how to read this. The I means imaginary. This means reduced. I'll tell you what reduced means. You don't want to be saying things like, I'll just explain to you what these terms mean. It's actually not difficult once you know what these poor men are forced to. This should not exist. And I'll tell you what it actually means without you even having to know anything about it. It's the linearization of a spherical function. This represents the linearization of a spherical, I'll say function, but it's actually a spherical system. And it is spherical, they know that. But here's the problem. All of these scientists are convinced that linear algebra can reach this kind of thing. Obviously, it can't. I'm going to show you why not and the solution to all of this. And then we're going to get all of these solutions in understandable form and the Einstein field equation, which is much easier than this, I'll say. This is the imaginary, reduced, linearized psi function, which is actually a 4 number. It's a 4D number. 4D means it has 4 numbers in it that are all linear numbers because they all represent orthogonal lines. And the 4th one is the killer because it's imaginary. And that's why you have I. You're always going to have an I in these equations somewhere because of the ridiculous way that Einstein was forced to make this linearization of spherical space. He had to invert the valence of the time axis. So it has a negative valence, whereas the spatial axes are positive. And that that destroys any hope of understanding it. Not completely, because it has to have a geometry or it wouldn't work. I found out how it works. You may already know it's hyperbolic geometry for the Einstein field equation. What is this? Well, it is also a four-axis system. It's called a four-component number system. And Paul Dirac used a very famous shortcut, which you're always allowed to use, called complex numbers. Now, all of that is hidden in here. It's like the Einstein field equation. You look at it, and it's just about this long. And you look at it, and you think, well, it couldn't take too long to learn. That's what I thought about the Einstein field equation. Yeah, it takes a long time just to learn what it even says, let alone what it means. But I've become quite adept at doing this. This is the imaginary, reduced, linearized psi. So you could also say this is the imaginary, reduced, derivative of psi. This on the other side is just psi. So this is the relationship between psi, which is a value. It's a 4D value. And it's equivalent to the derivative of that value on this side. So this is the equation of equivalence between the psi function and its derivative. For the derivative of the psi function, it's the imaginary reduced form of psi. On this side, it's not imaginary, it's not reduced, and it's not derived. This is integral psi with respect to this psi. Or you could say that this is the derivative psi with respect to this psi. But the relationship between these two is the calculus. It's the calculus relationship between, that's what this curly D means. It means there's a relationship between this side and this side. And on this side, you're taking a calculus derivative. You can invert that because the fundamental law of calculus is that the integral is the exact inverse of the derivative. That has been argued for 3 centuries, and if you wish to join in, spare me, because I know more about it than you'll ever know. And I'll try to share that with you so you can be just as pompous as I am. All right, so this is psi, and this is the derivative of psi. And that's all this is the derivative of psi. And these are the converters that make it into the right form to match this side. So when you take the derivative of psi, you also have to reduce it and then imaginify it. And once you have an imaginary reduced derivative of psi, you can use this to find out how this turns psi into its derivative. So this is an extremely valuable function because it establishes a relationship between the psi function and its derivative. Now, what is the psi function? And this is just the tip of the iceberg, but that's what I wrote here. Oops, I keep doing that. Let me put that back. Okay, so what we need is to understand this. No, we don't need to understand that. All we need to understand is what this formula actually says. You don't need to know what's in here because it's inside of these. Those are called braces, or parentheses in American English. I think that's international. So the psi function on space and time is a complex four-component field that Dirac thought of as the wave function for the electron. R and T are the space and time coordinates. The R has 3 spatial components, and the T is negative time, as you know. That's called the Einstein signature. I'll show you that there are about 16 names for that signature, because this is an extremely confused, convoluted, absolutely uncoordinated, basically leading nowhere for 70 years. You could make it 100 years. And this actually does not ultimately help. Although it will once it's translated into the right geometry. All of the progress that we've made, both in cosmic science, which is astrophysics, you can exclude the cosmologists. They're simply guessing. Astrophysicists are not guessing. They're taking educated guesses. The cosmologists are not. They're taking uneducated guesses. And you never want to dabble in cosmology because it's never right. But astrophysics, although it hasn't been able to get very far, at least it has the facts and at least it has the knowledge. So far, no one has any understanding of deep space science. None. None. They don't know what to do next. And it's been like that for a century. Zero progress. And there can only be one reason for that. A fundamental mistake in the way we've approached the universe. And I'm going to show you what that is so I don't have to keep saying it. I'm going to show you. This right here is the coefficient of psi. So you can forget it. This is psi equals the derivative of psi. Now, psi does not equal the derivative of psi. You're going to have coefficients. And that's all this, and this are. They're coefficients that equate the psi function with its derivative. And the way that that's done, and I can now state what this says, that whatever this does to psi, on the other side, for the derivative of psi, it will equal the imaginary reduced form of the derivative of psi. The imaginary reduced derivative of psi equals psi times this. And that should be valuable, but before it could be valuable, you have to know what it means. And nobody does. So, the rest is just explaining what nobody understands so that you'll know what they don't understand either. And here, this tells you what alpha is, that thing right there. Look at that. Alpha is composed of these 3 components, each of which is a 4x4 matrix. And beta, this one, is also a 4x4 matrix. But look at that alpha function. And this is momentum. There's no need for you to spend 4 years to learn that. You know everything that they know about it. I just told you what it means. The algebraic structure had been created by Clifford, emerging from Grassmann's Die lineale Ausdehnungslehre, a legendary book. This is one of the most remarkable chapters in the history of physics. That's absolutely true. Is that Dirac got this from Grassmann. That was a century before Dirac. Not quite, but almost. Clifford lived in the 1870s. Die lineale Ausdehnungslehre was published in 1844. Dirac is explaining a relativistically moving electron, another not understood anything, consistently with relativity. You see, that's what they're actually trying to get. And Dirac made a major insight, but it's written in linear algebra ease. It's written in calculusite. It's written in calculesia. It cannot be understood because it's not understandable. And so this is the most important statement in this article, which is from a blog site, which I'll give the link for that. Discretizing the angular momentum of the electron's orbit had failed. That is the problem. That is the only problem. And it's well stated, and this also affects the Big Bang theory, the black hole theory, the theory of galaxy evolution, and everything else in astrophysics, and everything else in atomic physics. Everything is affected by this. Is that the angular momentum value cannot be computed. They can't do it. Everything is based on angular momentum. Everything is based on angular momentum in the whole universe. Angular momentum is the direct expression of energy. Max Planck proved that. But you notice it's angular. You know what that means? It means it's not linear algebra. And you might think, well, maybe we should just change to the right algebra. You would be right. What would that mean? Well, it would take a really remarkable discoverer to find out the correct algebra. I did. That's what I discovered. Is the correct algebra. So, the quantum mechanics of Heisenberg, Pauli, Jordan, Schrödinger, and Dirac himself had made no progress. It still hasn't. His equation had far deeper implications for the structure of matter, so they think, and introduced new mathematical classes of objects. That's correct. It made it way more complicated. Just as the simple definition of gravity resulted in the most impossible to understand equation of all time, Einstein's field equation. But it's a tie. Dirac's equation is equally difficult, and they cannot be understood. They cannot be understood. So why are all of these equations being written? It's because we know we're close. But it's going to take a genius, someone who does not look like me or sound like me or do what I do. It's going to have to be someone other than myself who makes this discovery. But alas, it's too late. I got it. Now, this is another page. I just want you to see this. All right. Oh, it's tetrahedral.blogspot. Okay? So there's our equation right there. And here's how to read it. The right side can be, gone through that. So I'm going to go down here. Right here. Time space. I abbreviate a lot of things in my writings. Small t, capital S, that's called camelback, and it means time space. There are, in time space diagrams, are 4D diagrams, which you can imagine you'd have to really be clever. It can't be shown, but it can be projected down to a 3D. And from that you get what's called the light cone, and then you have 3 different intervals. Time-like, light-like, and space-like. Don't worry about understanding this. Classify 1D curves through curved spacetime. Similar to the error missed in string theory. Okay, this line here, the error of dimensioned linearity, that's my discovery, and this one, the error of assumed linearity. These are the two mistakes that describe all of physics today. are based on these two errors. When I compare time-space with the string theory, that needs to be explained. String theory is considered now to have missed the mark. We all knew that at the beginning, but nobody knew why it would miss the mark. It just smelled wrong, and sure enough, now it stinks to high heaven. Nobody gives a hoot about string theory any longer. Why? Because it's no different from space-time. It's a reformulation of space-time, making the same mistake that was made in space-time. You're trying to bend a straight line. That's all you need to know about string theory, and that's all you need to know about space-time for now. Space-time, however, is a much different animal. But the error that was made in string theory, I call the error of dimensioned linearity. In other words, a line is always straight, correct? Well, what if you try to pluck it? I actually made this mistake in part of my research last spring, and it took me a while to come out of it before I realized that I was making the same mistake that the string theorists had made. I was trying to establish a harmonic on the sphere by a pluck. Well, that actually changes the sphere. Now, it might be physically true that the sphere is not exactly a perfect sphere, but currently we have no reason to believe that. And so that's a red herring. But it's interesting to notice that I made the same mistake that the string theorists made. But this matter of the time-like, light-like, and space-like intervals of classical space-time, this is what all of them use. All of the astrophysicists use this space-time interval. And it's wrong. But why is it wrong? It's because it's linearized. It's linearized, and 4D is the wrong answer. And so they're using the wrong geometry. They're using 4D. 4D cannot work. It's 4 lines. These aren't lines, children. This cannot be linearized. And so that's the mistake. Now, there's another mistake called the error of assumed linearity. I'll cover that in a while, but for now, well, actually, I should tell you what that means. Why am I citing two different errors? They're closely related. When you're using a straight line, that has all the numbers on it. When you compose space or you try to compute anything, you just add more lines. When we're done, when we had 3D, that lasted 2,000 years. But then Einstein used 4D to get the definition of gravity. And both of those are the linear solutions. And that's why nobody can understand them. So James Maxwell used 4D to compose electrodynamics. That works for electrical engineering. And that's all it works for. Because then you can use calculus. These two errors of mistaking the linearity of the system for something that they can fix leads to the Erlin-dim and Erlin-ass. And if you put them together, that's dim-ass. And so the way I pronounce that is airliner. In other words, if I catch you, which I've caught them all, using linear algebra to compute quantum mechanics or astrophysics, then I get to look at you and laugh and point my finger and say, well, I guess you didn't go to school then. That's a real airliner. A real airliner. I have a vendetta. I'm trying to get rid of it, but it's going to take a while, man. I admire each man individually. They have been struggling like trying to swim up a waterfall. And they've worked miracles in trying to get sticks, Greek sticks, to explain things in heaven. only a monkey